about Colmena.
Right, good afternoon, everybody. So I'm Logan Ward. I've been working with Kyle and Yadu for about 4 years now on a variety of projects. But the most recent one that I've come here to talk to you guys about today is a project I'm working on as part of the exascale computing project's ExaLearn. And okay, I'm sharing screen, you're hopefully seeing PowerPoint.
You might need to present. It's not zoomed in. Okay.
Okay.
Yep.
Working?
Yep.
Excellent. So as I mentioned, Colmena is a part of the exascale computing project and has been something that I've been working on over the past couple of years with the Parcel team and many others at Argonne, UC, and quite a few other institutions to figure out how we build this tool and make it available and make it tuned for different scientific applications. So now that I've said the name of our tool a few times, we'll get into what we actually designed this thing for. And our key motivation was looking for the fact that while high throughput simulations are a common use on HPC, they're not actually a great use of high performance computing resources. And the key issue with this is the ways that how we're deciding what to run on the supercomputer is often limited by the human in the loop. For instance, your typical high throughput campaign might look a little bit like this, where I have a task generation step that's performed by a human to decide what to run on the supercomputer. After that finishes, a couple of days later, that human might come up with another queue of tasks. And this process iterates. And the big problem that we're looking at is with supercomputers increasing by tens and hundreds folds in the rates that they can give us new data, humans are not getting any better at processing it. So what we're trying to do is come up with a series of tools that will allow us to build applications that autonomously steer high throughput simulations on HPC. And this can turn out to be a problem, given the fact that there are many different ways you could envision how a steering algorithm and the simulations it's invoking cooperate together. Especially if this is in the situation, which is common in many high throughput cases, where running a sequential search is impractical because no single code will scale to use the entire HPC. And you can come up with strategies like, well, I'll wait for a batch to finish, then I'll pick new tasks. This yields utilization problems. Or I can maintain a list of tasks, always have one ready to submit, but here I'm not using the most amount of information to decide how I want to use that supercomputing resources. So hopefully you believe me here that the ways for using HPC and coupling it together with a steering algorithm are not clear-cut. And there's a lot of potential opportunities for coming up with intelligent applications to balance these different needs of being able to run many simulations in parallel and with keeping them informed by the best logic to determine what to run next. Colmena has been our approach for being able to do that. And one of the things we noticed right away was the kind of strategies that we could come up with for doing this HPC steering were quite diverse. We could have simple event-based logic, like when one simulation completes, submit another. We could have conditional logic, like retrain models after 8 simulations complete successfully, or things dealing with resource management. And these are just 3 strategies that one might use when developing a steering program. And this was enough to convince us that we weren't going to build a solution where one could write a specification file that contained all of your logic in YAML or some other markup language of choice. Rather, we need some way of being able to write programs that define the software in a programming language. So to that end, we came up with a tool called Colmena, which really at the scheme of things is just a wrapper over exascale workflow tools, namely Parcel, that allows you to program these steering processes as a series of interacting agents that interface with a supercomputer via a task queue system, with the idea that you write tasks to send to some sort of workflow engine like Parcel that executes your data remotely on a supercomputer, and then the results eventually trickle back to the thinking algorithm, which can then decide what sort of new work to submit based on what has completed. The code is written for writing these steering algorithms is Python. We've built a series of helper classes that let you define a thinking program that could be composed of multiple kinds of agents, such that when you instantiate it, you can define what variables are shared knowledge between the different agents, such as how many guesses the system is allowed to make. And then you can have a series of interacting policies like a result consumer that executes some logic whenever a simulation completes, or a task producer, which runs a separate set of calculations to determine what the next best simulation could be. If you couple this with a task engine, ours is built on top of Parcel, which sits at the other end of the queue and executes the work, you can build applications which intelligently use HPC and, as I'll soon demonstrate, can scale to thousands of nodes. And that's pretty much exactly what we've done in some of our initial work with Colmena. We ended up creating this complex application where I run 3 different types of compute operations on a supercomputer, depending on the state of the search. For example, I have 2 sets of agents which submit NWChem calculations to run on the HPC or retrieve their completed results and store them to a database, tools which update the models based on the recent database, and policies which take the most recent models, use their inference to update a molecule queue. And what you can end up getting with this kind of complex application is a behavior where we can illustrate changes in how our resources are utilized as a function of time. Here, you're seeing how we utilized 1024 nodes on Theta over a 6-hour allocation. And you'll note how we've written our application to start off by running inference tasks on all of the nodes. Once those complete, I switch over to using simulation on every available resource, and then dynamically switch between retraining models on some of the resources, using those updated models to reprioritize my task queue. And at some point, once I'm done reordering the task list, go back to dedicating everything towards simulation. And what we've been able to find in this chart, where I'm showing the number of good molecules we found as a function of time, that this complex policy for dynamically reallocating resources yielded finding about 10% more molecules given the same amount of computational resources than a policy which kept those machine learning models stagnant and did not update them over time. We've also been able to find some opportunities for improving the utilization of supercomputers. Most of them have to do with writing more intelligent policies, such as avoid running particularly long NWChem calculations towards the end of your allocation time, or coming up with ways to perhaps offset the large startup costs it takes to bring a new TensorFlow computation online. So that wraps up my talk today, and I've hopefully stayed within my 7-minute budget. So in conclusion, today I've talked to you about a code we're building, Colmena, that allows you to come up with complex policies for deploying a dynamic mix of simulations on HPC, along with the AI calculations needed to determine which simulations would be the most valuable. And this is an open source code we've built on top of Parcel. It's all pure Python and is available open source on GitHub, also on Read the Docs. And if this is something that's interesting you, I will gladly help you get started on this kind of rather new code for us, and would be more than happy to receive any complaints from you about it. So at this point, I'd like to thank all my collaborators, many of whom are on the call today, and would be happy to take any of your questions.
Thanks, Logan. I have a question to start off the session with. Can you tell me a little bit about what are the outstanding challenges that is still out there? Maybe something about the data components or the latency components, or what is that to improve?
Absolutely. So if I were to go back to this chart here, the one big grievance that I have with Python apps on HPC is the amount of startup time it takes. It takes about a minute to load in TensorFlow. So any sort of capabilities within Parcel that help us use technologies like Conda Pack to move Python environments out to a compute node more efficiently would be extremely welcome. Additionally, and unfortunately, I believe I dropped the slides and I don't have them in my backup. We also see some latency in sending large data objects to nodes from the mom node on a Cray supercomputer. So I don't know if that's a niche problem that we have on Theta or something that's spread across more supercomputing systems, but having some mechanism for sending large data objects along with Parcel would be very beneficial.
Logan, a quick question. Along with this programmatic way of taking a task pool and dynamically determining task runability and things, do you also have any kind of declarative dependency mechanisms other than plain Parcel built into Colmena?
So what do you mean about the, I'm afraid I might have a terminology question. What do you mean about these dependencies? Are these like stringing jobs together?
Yeah, declaring, basically forming, DAG-like dependencies or, data flow dependencies that are not programmatic, but just, declared as,
I would, that's been something that we've been tinkering around with, thinking that perhaps you may want to string a series of jobs together and have some way of just describing that rather than implementing the logic of one task comes back, send another. But unfortunately, that isn't something we figured out how to do cleanly yet.
Got it.
But thanks for the question.
Has this been applied to domains other than material science and molecular modeling?
No, our other use case that we've dumped a lot of time into is also material science. Liquid salts rather than electrolytes for batteries, but probably for the intent of this conversation, it's all materials engineering.
Thanks.
Thank you.